Okay, so welcome back. In this particular video, we will be discussing the problem number of prime numbers less than n. So let's read what is the problem statement asking us to do. The problem statement: count the number of prime numbers which are less than a non-negative integer n. So we are given a positive integer. Non-negative means anything which is greater than 0. So a value which is greater than 0, and we have to count all the numbers which are prime lesser than that particular element n. So input will be a single integer as told, and output will also be an integer, that is the number of prime numbers. So if let's say there are input n equal to 10, then how many numbers are there in between 1 to 9 which are prime? So we can say numbers which are prime are nothing but which do not have any other factor other than 1 and the number itself, that is numbers with exactly two factors, 1 and number itself will be the prime numbers. So from the range 1 to 9, what all numbers will be prime? I can say 1 is never a prime number. Why? Because 1 only have one factor, which is 1 itself. So 1 is not a prime. Is 2 a prime? Yes, 2 is surely a prime. Why? Because there are only two factors for 2, 1 and the number itself, that is 2. For 3, yes, again it is a prime because it only have two factors, 1 and 3. None other than 1 and 3 can divide 3 properly. What about 4? 4 is not a prime number. What about 5? Yes, 5 is a prime number because only two factors are there, 1 and 5. What about 6? No, 6 have a factor 2, have a factor 3. 7, yes, 7 is a prime number, only two factors, 1 and 7. Then 8 will have a factor 2, 9 will have a factor 3. So there are only 4 numbers in between 1 to 9, that is less than 10, having the condition true, that is they are prime. So output will be 4, that there are 4 numbers. So what the input can be? Input can be anything from 1 up till 10 raised to power 5. That is the input integer can be. We are about to be asked that the numbers which are prime can be in the range 0 till 0, or it can be in the range 0 till n minus 1, that is 0 till 10 raised to power 5 minus 1. So this is the problem statement. Now we have discussed the first milestone. Let's now jump on to the second milestone, that is nothing but discussing the possible approaches. So what is the most brute force approach which we can think, which we can come up with? I can surely say that if a number can have only two factors, exactly two factors, then it will be prime. So how about checking for each and every number whether it is a prime number in the range 1 to n minus 1? So I will be running a loop to each and every number in the range and then call a function or call a method to ask whether that number is prime or not. If that number will be prime, it will return true. If it will return true, I will do count plus plus. I will say that yes, it is a prime number. Otherwise, if it will return false, I will not do count plus plus. I will say the number of count numbers, prime numbers are same. So if I take an example of the same n integer, which is 10 only, let's take a dry run. So if n is 10, what we are saying, check and start from the number 1. But actually, should we start from 1? Can 1 be a prime number? No, 1 can never be a prime number. So better will be to start checking from 2. Is it 2 a prime number? Then 3, then 4, then 5, then 6, 7, 8, up till less than 10. That is up till 9 in this case. So how we can check whether a number is prime? We will be checking how many factors does it have. A number which is prime will have only two factors. So let's say initially for 2, the number of factors are nothing but 0. There are 0 factors. And I will start checking to divide 2 by all the numbers possible. So is it 2 modulus 1 0? Yes, 2 modulus 1 is 0. That is to have a factor 1. And since to have a factor 1, we will say number of factors from 0 will become 1. That is first factor of 2 has been occurred. Now I will check for 2. Is it 2 modulus 2 also 0? Yes, it is also 0. So number of factors will become 2. And since there are exactly two factors, answer will be true. And I can say if answer is true, count, that is number of prime numbers, will become 0 to 1. That is count will become plus plus. What for 3? I will again say that call the function whether 3 is a prime factor or not, prime number or not. So initially the number of factors will be 0. And I will try to check for each and every number by dividing that 3 number with the corresponding loop, that is 3 modulus 1, 3 modulus 2, 3 modulus 3, up till the number itself, because factors are always lesser than or equal to the number. So I will first check, is 3 modulus 1 0? Yes. So factors plus plus. Is 3 modulus 2 0? Can 3 be divided by 2? Is it 2 a factor of 3? No. What about 3? Yes, 3 can be divided by 3. So I will say count of factors plus plus. And again, since there are two factors only, we will say the number 3 is a factor which is a number which is actually prime. So I will say count plus plus similarly. So what for 4? For 4, initially, we will say number of factors are 0. For modulus 1, is it 0? Yes. So number of factors plus plus. For modulus 2, is it 0? Yes. Number of factors plus plus again. For modulus 3, is it 0? No. So do not do increase of the number of factors. But as soon as I go to 4 modulus 4, the number of factors will become 3. That is, it will become more than 2. And if it is becoming more than 2, it is not a prime number. And if it is not a prime number, we will not increase the count. That number of prime numbers till 4 are only 2. Similarly, we will do the same job for 5. We will do the same job for 6. 6 will not be a prime. So for 5, it will be prime. So count plus plus. 7 will be a prime. So again count plus plus. 8 will not be prime. 9 will not be prime. So what will be the time complexity for this kind of brute force? If I am applying this brute force where I am checking for every number by trying to divide all the numbers from 1 up till the number itself. Since for each number, I am running a single loop, a linear loop. How many numbers I am running a loop? For n numbers. 2 times for this, 3 times for this, 4 times for this, 5 times for this in worst case. So 2 plus 3 plus 4 plus 5 up till n. It will go n into n plus 1 by 2. That is order of n square. So brute force time complexity will be order of n square. That is quadratic. Reason being there are nested loops. First loop to check for each and every number that whether it is prime or not. And second loop, a linear loop again to check how many factors are there for a given number. And what about space complexity? Are we going to use any extra space complexity? Actually, no. We will be able to do it in constant space because we are not storing anything in any kind of data structure or string or something. So can there be a better approach? Can we optimize this? And answer is surely we can, but we have to see a mathematical proof for that or a mathematical observation for that. So if I take any number, if I take, let's say, a number 32. So what are the factors of 32? Although 32 is not a prime number, but let's try to figure out the factors of 32. There are factors 1, then you can say 2, then you can say 3 is not a factor, but 4 is 4 a factor? Yes, 4 is a factor. Then what about 6? Is 6 a factor? No. What about 8? 8 is a factor? Yes. What about I guess 9? No, 9 is not a factor. Then what is the next factor? We can say, like, if we start from last, surely we can say 32 is a factor. I can also say 16 is a factor. Is there any other factor which is possible? I guess no. All these are the factors of 32. So what is the observation? See, if 1 is a factor of 32, if 1 is a factor of 32, surely the number divided by 1 will also be a factor. That is, 32 divided by 1 will also be a factor. Same goes with if 2 is a factor of 32. Same goes with the 32 divided by 2. That is nothing but 32 divided by 2 is 16 will also be a factor. Similarly, if 4 is a factor, then I can on the same ground say that if 4 is a factor, then 32 divided by 4, that is 8 is also a factor. So this is the observation that if number x is a factor, if number x is a factor, then number n minus x is also a factor. If I am saying that number n is 32. So applying this procedure for few more numbers, if I take n as 25, what will happen for 25? I can surely say that 1 is a factor. So 25 divided by 1, 25 will also be a factor. What next? I guess 2 is not a factor, 3 is not a factor, 4 is not a factor. What about 5? If 5 is a factor, 25 divided by 5, that is 5 will again be a factor. That is, both the pairs will be actually the same. So the observation is, since every factor exists in pairs, every factor exists in pairs, every factor exists in pair, what we can surely say that if we are checking a factor up till the half, no need to check for the remaining half. If there is a factor in the left half, surely there will be a factor in right half. If there will be no factor in the left half, surely there will be no factor in the right half. Let's say if I am saying n is a prime number, let's say n is a 17. So for 17, what in the brute force we were doing, in the brute force solution, we were running a loop for 1 to 17, all the numbers, 17 modulus 1, 17 modulus 2, 17 modulus 3, up till 17 modulus 17. Why? Because we have to check how many factors of 17 are there. But now what we are doing, since all the factors always exist in pair, we are based on this property saying that if there will be a factor less than the half of the range, then there will be a factor in the right half also. But if there will be no factor in the left half, then there will be no factor in the right half also. So what is the left half, what is the right half? In this case, what was the left, what was the right? In this case, what was the left, what was the right? In this case, you can surely see that there is 5 as the middle point. All the elements in the left will be lesser than equal to 5. All the elements in the right will be greater than equal to 5. Similarly here, what it will be? Actually, it will be in between 4 and 8. So just on a observation basis, you can say it will be approximately a root of 32. The middle value will be root of 32. That is, it will come out to be approximately, you can say, around 5 point something. But if 5 is not a factor, then obviously the other number will also be not a factor. So what we can say, the biggest number up till 5, we have to check all till that number only. So if I am taking example of maybe n equal to 36, for 36, till which number should I check? I will only check for numbers till root of 36, that is only till 6. Why? Because if 1 is a factor, 36 divided by 1, that is 36 is also a factor. If 2 is a factor of 36, 36 divided by 218 is also a factor. If 3 is a factor, 36 divided by 3, which is, you can say, 12 is also a factor. What about 4? 36 by 4, 9 will also be a factor. But as soon as I go to 6, 36 by 6 will become equal to 6. So at this point, we are merging. So 6, if it is equal to 36 by 6, 6, if it is equal to 36 by 6, then what we can say? 6 is a square root, obviously. If x is equals to n by x, then we can surely say x is equals to root n. Why? Because x square equal to n. So from this observation, what we can say that no need to check whether a number is a factor up till the number n. We can only go till root n. So I will check for root of 17. That is only till I will check till 4 point something. That is I will check till 5. Or you can say till 4, like whatever you can take. You can take the floor value, you can take the seal value, you can take anything. By default, it is always floor division. So you can take floor division. So what we can say is 1 a factor of 17? Yes, but we should not check for 1 because 1 and 17 itself will also always be a factor. We will start from 2. Is it 2 a factor of 17? No. Is it 3 a factor of 17? No, because 17 modulus 3 is not 0. Is it 4 a factor of 17? No. And if there is no factor from 2 till 4, there will be no factor from 5 till 16 also. And this I can say for sure. Why? Because if there is no factor in the left, there will be no factor in the right, because all the factors exist in pairs. So on this observation basis, what we can say, the time to check a number is prime or not, this loop has been reduced to root n time complexity. And the overall outside loop or the outer loop is still linear, but inner loop is nothing but root n. So what will be the overall time complexity? It will be n into root n. For all the numbers, check whether it is prime or not. So checking a number is prime, root n. For all the numbers, linear loop. So it is nothing but n raised to power 3 by 2. Or you can say n into root n is the time complexity, which is better than the previous solution. So this was the optimized solution. I hope everyone has got the second milestone clearly, that how we are actually coming up to this observation. And let's now come up with the instruction manual in the milestone number 3. So first of all, what we need to do, we need to run a loop over all the numbers, over all the possible numbers in range possible numbers, in range what? In range 2 till n minus 1. Why? Because 1 can never be a prime number. Then to check whether a number is prime or not, we need to call a function. So call a function to check whether the current number num, let's say it is num, is a prime or not. If it is prime, then what should we do? We should increment the count. Where should we initialize the count? We should initialize the count before the loop, obviously. Increment the count by 1. So I will be saying initialize a integer count variable as 0. That is the number of count prime numbers less than n. And every time we will get a prime number, we will increase the count. Finally, what should we do? We should return the prime number, return the count of prime number, that is return the count integer. But in order to call the function to check whether it is prime or not, we will have to create a function, obviously, which will return either true or false. So public boolean is a prime to check whether a number is prime or not. And I will pass the number num to check whether it is prime or not. And how we can check whether it is prime or not? We can say run a loop again, but this time only till root n. Run a loop over all the numbers till root n. And how we can actually run a loop till root n? We can say that for 17, we should run till only 4. Is 1 into 1 less than equal to 17? Yes. So run the loop for 1. 2 into 2, is it less than equal to 17? Yes. Run the loop for 2. 3 into 3 is less than equal to 17? Yes. So 3 is also within the root. Is 4 into 4 less than equal to 17? Yes. But as soon as I go to 5, 5 into 5 is more than 17. So do not run the loop. So what we have to do? We only have to run the loop till the current, you can say, number which we are trying to divide, the factor, till the factor is nothing but less than the root. So run a loop over all the numbers, over all the factors possible till root n, till only root n we have to do. And how we can run the loop till root n? We can say that is till factor into factor is less than equal to the number itself, or you can say the number which we are trying to check whether it is prime or not. So till this point we have to run the loop. And every time what should we check? We should check that whether our number is able to divide the number num or not. That is a factor of num or not. So if num is completely divided by factor, num is completely divided by factor, then what should we do? We should return false, that number is not a prime. Otherwise, number is prime. So we can say return true finally after the loop. So should we start this loop from 1? No, we should not start this loop from 1. We should start all the factors possible till root n from 2, because if we will try to divide by 1, obviously every number will get divided by 1. So we will try to start or search a factor from 2 till root n. If there is a factor, then number is not prime, otherwise number is prime. So this is the instruction manual which we have come in the milestone number 3. We will be coding the solution number of prime numbers less than n. And now we will be doing the 4th milestone, that is inline expanding the code in Java programming language. So we had 2 functions. First function was checking whether a number was prime or not. So what we have to do to check whether a number is prime? We can run a loop over all the numbers till starting from 2 till root n. That is till factor into factor is less than equal to number itself or not. And for all the numbers, we have to do factor plus plus. And now what we should do? We should check whether that number is completely divided by the factor or not. That is the modulus by factor is 0 or not. So if number modulus factor will be 0, then what should we do? We should return false, that number num is not a prime number. So return false. Otherwise, if all the loop runs, never we are able to return false, then obviously we are going to return true, that is number is a prime number, because there is no factor in the range 2 till root n. So this is the is prime function taking order of root n time complexity. What about count primes? Before running this loop, let's try to check whether the is a prime function is working properly or not using system.out.println is a prime of, let's say, 2. Is it 2 a prime number or not? Let's see. So if I just run this and we have to return something. So for now, let's return 0. Otherwise, there will be error. So let's see if is a prime of 2 will give me true or false. Ideally, it should give me false because, sorry, actually true, because 2 is a prime number. So yes, it is giving me true for 2. What about 17? 17 is also a prime number according to my knowledge. So it should also give true. Obviously the output will be false because we have to print the count. We are not doing it, but output we are getting is true. But what about 18? Is 18 a prime number? Or maybe let's take 25. Is 25 a prime number? No, it should have a factor root 5. That is root 25 actually, that is 5. So it should not give me true. It should give me false. And it is giving me false. So is a prime function is working properly. Let's now do what? Let's now code the main logic. That is counting the number of primes. That is a simple logic. Just initialize the count from 0, run a loop over all the numbers starting from 2, because 1 can never be a prime. going less than n, that is n minus 1, number plus plus, and we will check for each and every number whether it is prime or not. So if the current number is prime, that is a prime of num is a true. If the current number is prime, then what should we do? We should increment the count by 1. That is count plus plus. And finally, we should return the number of prime numbers, that is count variable. Let's now try to see it for the sample test case. For 10 numbers, answer should be 4 because the prime numbers are 2, 3, 5, and 7. Yes, it is giving me false, basically 4. What about a test case where I am saying there is only n as 1? So how many numbers are there which are prime from 0 till less than 1? 0 numbers are there. The output will be 0. What about a very big number? Let's say for 10 raised to power 5. Let's try to run this code for checking whether our logic is not like giving any kind of runtime error or something. So it is giving me output. Expected output is also 9592. My output is also 9592. Let's try to submit now to see if it is actually working all test cases. And yes, it is working for all the boundary cases as well. So with that, we have discussed the fourth milestone, that is instruction manual, along with the fifth one, that is how we can come up to this approach using some sample test cases, corner test cases. But one thing from my side will be a follow-up question. See, till now, what we have done, we have solved this problem using a simple iterative solution that we have checked for each and every number, whether that is prime or not. A better solution will be to store all the prime numbers in a certain data structure, in maybe an array or in maybe a certain kind of set, so that we can check whether a number is prime. If it is, mark all the multiples of that prime as non-prime. Similarly, for all the other numbers, like let's say for 2, let's say for 3, let's say for 5, and so on. And in this way, you will be able to solve it in even lesser time complexity. And that algorithm where you are going to basically store all the prime numbers in an array or a set will be known as a sieve of Eratosthenes. So just try to follow that strategy. Just try to come up to the approach for that sieve algorithm. You can read about it in the articles given in the resources section. And till then, you can code this particular solution, which is taking n root n time complexity. So let's meet in the next one. Bye bye.